Today I'd like to talk to you about thermodynamic potentials. I would like to introduce a new way of characterizing equilibria. What we've done so far is that we said when you're given certain macroscopic data relating to constants of the motion, to all the constants of the motion, then the equilibrium state is that state which, under these given constraints, maximizes the entropy. So a little reminder of the maximum entropy principle. We have an isolated system. We are given macroscopic data, particle number, volume, internal energy, and others. Then the equilibrium macrostate is that state which, under these constraints, maximizes the entropy. We've also seen already a symbolic representation of this principle graphically in state space. Let's assume that volume and particle number are given as sharp constraints, they are fixed, and let's assume that energy is given as an expectation value. So we are in the canonical case. Then just a conceptual pictorial representation of the situation is as follows. Once again, I would like to draw lines of constant entropy. So each line corresponds to a constant entropy. Let's say that the entropy increases in this direction. Now, if we are given volume and particle number are fixed anyway as sharp constraints, but if we are now given, in addition, the expectation value of the energy, then this, of course, doesn't specify the state uniquely. There are many states that have the same expectation value for the energy. Let me indicate with this blue line the set of all states that give the same expectation value U for the internal energy. Then we said there is a unique state, and that's our macrostate, so our equilibrium macrostate. There's a unique state in this subspace represented by the blue line, which maximizes the entropy. And it's this state here. This is the macrostate, and here it's a canonical state. Why is this state unique? We gave a mathematical proof early in the semester when we talked about how to construct a macrostate. I'd like to just give another heuristic argument so that you can visualize the argument. I personally always like to visualize things. So it's not a strict mathematical argument, but it's an attempt to make it plausible with the help of this little conceptual drawing. The blue line, so the subspace of all states with the same internal energy expectation value, these form a linear subspace of state space. In the following sense, that if you have two states, rho 1 and rho 2, which both satisfy the given constraint, so they both lie in the subspace, then any linear combination of rho 1 and rho 2, so lambda times rho 1 plus 1 minus lambda times rho 2, lambda is between 0 and 1, any such linear combination also satisfies the constraint, gives the same expectation value. This is a simple consequence of the fact that the expectation value is linear in the statistical operator. It's the trace of rho times h. And if two different rows give this expectation value, then any linear combination also gives this expectation value. So the states satisfying the given constraint, the expectation value constraint, they form a linear subspace. In contrast, the lines of constant entropy in a higher dimensional state space, these are hypersurfaces. They are curved, they are not linear subspaces. And in particular, they have the property that if you take two states, let me call them again rho 1 and rho 2, on the same hypersurface of constant entropy, then let's see what happens to any linear combination. So let's look at the linear combination here. And let's look at the entropy of this linear combination. This linear combination, so lambda times rho 1 plus 1 minus lambda times rho 2, where lambda is between 0 and 1, by the general properties of entropy, which we had listed when we discussed the concept of entropy, mixing of two states, so forming a linear combination of two states is called mixing, and mixing two states always increases entropy. So this is strictly larger than S of rho 1 or S of rho 2. I mean, they are from the same hypersurface, so they have the same entropy. But for any lambda in the open set from 0 to 1, so lambda is not equal to 0 and not equal to 1, but it's in between 0 and 1. For any such lambda, and of course rho 1 different from rho 2, the entropy will be of the linear combination of the two states will be strictly larger than the entropy of any individual of these two states, assuming that they rho 1, rho 2 have the same entropy, lie on the same hypersurface. Now, this property ensures that if you look at all states with an entropy larger than any a given value, for example, all states with an entropy larger than the entropy of these two states, rho 1 and rho 2. This would be, in this graphical representation, here this whole shaded area. This shaded area encompasses all states that have an entropy larger than the entropy of rho 1 and rho 2. And due to this property that mixing increases the entropy, this set is convex. It's a convex set in state space, whereas the set of states satisfying the constraint, symbolized by the blue line, this is a linear subspace. Now, the equilibrium state is then the unique state where this linear subspace is tangent to this convex set. And so I hope you can see it in this two-dimensional representation that given the convexity of this set of states with a given entropy bound and the linearity of the subspace of the states satisfying the constraint, I hope you can, it's plausible from this pictorial representation that there should be a unique state of maximum entropy in the linear subspace. This is, as I said, not a mathematical proof, but an attempt to visualize the argument. Now, I did this in order to prepare you for a change of perspective. Let me draw the same state space again. Let me now indicate just a single such curve of states of constant entropy. This is our original subspace of states of constant internal energy. Here was our macro state. And now I would like to draw a few more blue lines representing different expectation values of the energy. Another line here, another line there. These lines are parallel. These subspaces don't intersect. Remember the direction in which the entropy increased towards the interior of this convex set. Now the energy must increase in this direction because at a given particle number and volume, higher energy means higher entropy and vice versa. This is due to the fact that the temperature is positive. The temperature is the partial derivative of internal energy with respect to entropy at given particle number and volume. And this is strictly positive. Therefore, the energy must increase in the same direction in which the entropy increases. So just as a reminder that the temperature, which is the partial, this partial is strictly positive. So energy must increase in that direction. Now this graph, this picture, allows a different interpretation, a different characterization of the macro state. Because you can also say, at given entropy, so given this gray line, entropy is now given. Rather than on the previous picture, energy was given, and the macro state was characterized as that state which at given energy had the maximum entropy. Now let's say now entropy is given. So this gray line is given. Let's look at different states on this gray line. Let's look, for example, at this state here. This state has, given the direction in which the energy increases, this state has a higher internal energy than the macro state. Also that state here has a higher energy than the macro state. The macro state is singled out as that state which, at given entropy, has the lowest energy. So we go from an entropy maximization principle to characterize equilibrium, to characterize the macro state. We go to an energy minimization principle, where we say at given entropy, we minimize the energy. So this is an alternative way of characterizing the macro state, the equilibrium macro state. This is, again, for an isolated system, so not coupled to reservoirs or other systems. The equilibrium macro state is then the state which, at given entropy, minimizes the energy. I hope that with these conceptual pictures, I could persuade you without a strict mathematical proof that this is another way of characterizing the equilibrium macro state. The advantage of this perspective is that it allows an easier transition, an easier motivation of the various thermodynamic potentials, because the various thermodynamic potentials that appear in classical thermodynamics are forms of energy, and not equal to the internal energy, but they are also energies defined in a slightly different way. And depending on the circumstances, depending on the setting of your experiment, the equilibrium state is always characterized as the minimum of one of these potentials. Here we minimize the internal energy, and this applies to an isolated system. Next, we will consider systems that are in contact with reservoirs, with heat baths or with a volume reservoir, and we ask how do we characterize equilibria for these non-isolated systems that are coupled to reservoirs, and it will turn out that it's precisely the minima of these thermodynamic potentials. Let's move on to the first of our thermodynamic potentials, which is the free energy, so-called free energy. And here we consider a situation where the system is no longer isolated, but it's coupled to a thermostat, which maintains a constant temperature of the system. So we have the thermostat, a heat reservoir at a constant temperature T of the reservoir. This heat bath is always in equilibrium, and it's coupled to our system. It may exchange heat with the system. In fact, this will be necessary to maintain a constant temperature of the system. And the system itself has fixed particle number and also fixed volume. Only exchange of heat is allowed. But the system itself is not necessarily in equilibrium. The system itself is an arbitrary state, and what we are looking for is precisely a way of characterizing the equilibrium state. So what distinguishes the equilibrium state from all other states that the system might be in? Only the reservoir is assumed to be always in equilibrium. How do we characterize equilibrium then? Well, we can consider the system and the reservoir together as a single large system, which then is an isolated system. So we can draw around this arrangement symbolically this little box. We have this combined system, this composite system, and this is then an isolated system. When we seek the state in which the system, the separate system, is in equilibrium, it's equivalent to searching equilibrium for the entire combined system of the system itself and the reservoir. Now the combined system is isolated, so our minimization principle for the internal energy applies that we had learned on the previous page. So for the combined system, we know that at fixed total entropy, since we talk about the combined system, we must add up the entropies of the system and the reservoir. So this is entropy of the system plus entropy of the reservoir. For the combined system, we must minimize the internal energy according to our minimization principle. So the total internal energy is again the sum of the system internal energy plus the reservoir internal energy, and this must be at a minimum. This is a way how we can characterize equilibrium now. This extremization principle, we can, by way of notation, we can write it in this way, that any variation, so any moving away from equilibrium, then any variation of total entropy, of total energy at fixed total entropy must be strictly larger than zero. So this notation means moving away from equilibrium at fixed total entropy. Now the reservoir is always in equilibrium. We assume that the reservoir is always in equilibrium, therefore for the reservoir, but not for the system, because the system is not assumed to be in equilibrium. Only for the reservoir, it holds that the change of internal energy of the reservoir, and such change of internal energy can only occur by exchange of heat with the system, so this is always in the form of heat. This change of internal energy of the reservoir is given by T ds, where T is also the temperature of the reservoir. So we can rewrite this extremization condition as variation of the system internal energy plus temperature of the reservoir times variation of the reservoir entropy must be strictly positive. Next, we exploit our condition that we are doing this variation at fixed total entropy. This implies that the variation of the entropy of the reservoir must equal minus the variation of the entropy of the system. Only then it's guaranteed that the total entropy remains unchanged. And furthermore, we exploit the fact that the reservoir is a thermostat, so it maintains a constant temperature, so the temperature of the reservoir doesn't change. The variation of the reservoir temperature is 0. Using these two ingredients, we find that the condition can again be rewritten as the variation of system internal energy minus temperature of the reservoir times variation of the entropy of the system, that this must be strictly positive. What's inside the square bracket, this we define as the free energy of the system. Free energy of the system, it depends on the temperature of the reservoir. It also, we never carried this explicitly, but let me write it explicitly here. The volume, which was assumed to be fixed, of the system. And then it depends, of course, on the state of the system, the density matrix rho of the system. This is defined as the internal energy of the system. So this is the expectation value of energy in the state of the system. So it depends on the state, the statistical operator of the system, which, remember, doesn't have to be an equilibrium state, minus the temperature of the reservoir, which is fixed. It's the temperature that's maintained by the heat bath, times the entropy of the system, which again is a function of the state of the system. So these two parameters, temperature of the reservoir and volume of the system, they are fixed by external constraints or reservoirs. So these are fixed. What can vary is the state of the system, and depending on the state of the system, you have a certain free energy. And this is the formula for the free energy. Now, the last condition that we had derived said that the equilibrium is characterized by a minimum of free energy. You know, this last line in black says that any variation of the free energy inside the square bracket going away from equilibrium increases the free energy. So in other words, the equilibrium is uniquely characterized by a minimum of free energy. So what we learned from this investigation is that the equilibrium state of the system minimizes the free energy. So you see in the previous case for an isolated system, equilibrium is characterized by minimum of internal energy. Now we have a system in contact with the thermostat, which maintains a constant temperature. And now the equilibrium of the system is characterized by a minimum of free energy. In the same manner, we can proceed now and go through the most common situations where you maintain constant temperature, that's what we just discussed, constant pressure, or a combination of both. You always seek a characterization of the equilibrium state, and you find that in each setting you have a different thermodynamic potential that is minimized. Let's move on to the next potential, which is the enthalpy. This applies to the situation where the system is coupled to a volume reservoir which maintains a constant pressure. So, a little sketch. We have here the reservoir, the volume reservoir, which maintains a constant pressure, P, of the reservoir, coupled to our system, and the two can exchange energy in the form of work. So there's no heat flow allowed, but there is, say, a movable wall between the two, and on one side there's the reservoir with a constant pressure, and this movable wall makes sure that the system also is under a constant pressure. So, in particular, the volume of the system is no longer fixed. Certainly the particle number, as always, is fixed. But what we fix instead is now the entropy of the system. Why is that? As in the case as in the two previous cases, we will characterize equilibrium as a minimization of energy at fixed total entropy. So entropy of the reservoir plus entropy of the system. Now the reservoir, as in the previous case, is assumed to be always in equilibrium. And the reservoir can only perform or receive work. But we learned that if you do work on a system, and the system is always in equilibrium, that corresponds to our quasi-static limit, then the work that you do is always reversible, so it doesn't lead to a change of entropy. Therefore, the entropy of the reservoir is constant. If now also the total entropy of reservoir plus system is fixed, then this implies that the entropy of the system must also be fixed. So maybe let me just add this as a little note here, as an explanatory note, that the reservoir exchanges no heat with the system. Therefore, the entropy of the reservoir is constant. Then we say that the total entropy of reservoir plus system is fixed. And this implies that also the entropy of the system itself is fixed. Now let's seek a characterization of equilibrium. We do the same trick as before in the case of the thermostat. We enclose system plus reservoir in a big box and say that this combined system is now an isolated system. So we say that at fixed total entropy, again, equilibrium is characterized as the minimum of total internal energy. So any variation away from equilibrium of total internal energy must be larger than 0. The reservoir is always in equilibrium, and energy is exchanged with the reservoir only in the form of work. This implies that the change of internal energy of the reservoir is given by minus the pressure of the reservoir times change of volume of the reservoir. So we can write the extremization condition, or the minimization condition, also in the form that variation of the internal energy of the system minus pressure of the reservoir times variation of the volume of the reservoir is strictly positive. Then we can say reservoir plus system combined form an isolated system, enclosed in a fixed total volume. So any change of the volume of the reservoir must be minus the change of the volume of the system. And so think of again as of this movable wall between reservoir and system. Together they are sort of enclosed in a huge container, and then there's this big pressure reservoir and a small system. They are separated by this movable wall, but when the wall moves, it doesn't change the total volume of system plus reservoir combined. Yeah? So this is the relationship between the variations of the volumes, and at the same time the volume reservoir has a constant pressure, so the pressure of the reservoir does not vary. Its variation is 0. This means that we can write this minimization principle in the form variation of internal energy of the system plus pressure of the reservoir times volume of the system. This is larger than 0. Inside the square bracket, we have now a new function h, which depends on two parameters which are controlled externally, the pressure of the reservoir and the entropy, because we said initially the entropy of the system is fixed, and it depends on the state of the system, and it's defined as the internal energy of the system, so that's a function of the state of the system, plus the pressure of the reservoir times the volume of the system. This function is called the enthalpy. And we learn that the equilibrium state is now characterized as the one which minimizes the enthalpy. So maybe just for completeness, a remark about the experimental setup. It's important to note that the system and the reservoir are not allowed to exchange heat, only work. So a situation that may correspond to the situation where you have a thermally insulated cylinder with a movable piston, and the piston itself is also thermally insulated. The piston is coupled to a reservoir that maintains a constant pressure, and inside, say, you have a gas. Yeah? So this is how you may experimentally realize such a situation. And due to thermal insulation, there is no heat flow between system and reservoir, and this ensures that also the entropy of the system is fixed externally. Now we proceed in a very similar fashion to understanding two more potentials. The next one is the free enthalpy. And this applies to situations where the system is coupled to both a thermostat and a volume reservoir. So here's a little drawing. I have a reservoir that maintains both a constant temperature and a constant pressure. It's coupled to the system, and in order to maintain a constant temperature, it must be able to exchange with the system energy in the form of heat. And in order to maintain a constant pressure, it must also be able to exchange with the system energy in the form of work. So there can be an exchange of both heat and work between the reservoir and the system. This is a situation with quite a significant practical importance, because whenever you perform, say, a chemical experiment in open air, in the atmosphere, then the atmosphere maintains a constant temperature and a constant pressure. So this is a situation that applies to, or may apply to, experiments in open air, because then you have temperature and pressure fixed by the atmosphere. We proceed in exactly the same fashion as before. At fixed total entropy, the equilibrium of the combined system, reservoir plus system, is characterized by a minimum of internal energy, again of the combined system. So we have variation of system internal energy plus reservoir internal energy is strictly positive. The reservoir is always in equilibrium as before. Therefore, the variation of internal energy of the reservoir can be written as temperature of the reservoir times change of the entropy of the reservoir minus pressure of the reservoir times change of volume of the reservoir. Also, in complete analogy with the previous cases, we can use that the total entropy of system and reservoir is held fixed. So the change of entropy of the reservoir must equal minus the change of entropy of the system. Secondly, the total volume of the combined system is fixed, so any change of volume of the reservoir equals minus the change of volume of the system. And finally, temperature and pressure of the reservoir are maintained at a constant value, so there is no variation of the reservoir temperature and no variation of the reservoir pressure. These are both equal to 0. Exploiting all these relations and proceeding in the same way as before, you find the extremization condition in the form that the variation of internal energy of the system minus temperature of the reservoir times entropy of the system plus pressure of the reservoir times volume of the system, that this must be larger than 0. And now inside the square bracket we have yet another function which we call g. It depends on two parameters which are fixed externally, namely the temperature of the reservoir and the pressure of the reservoir, and it depends on the state of the system. and it's defined as internal energy of the system, which depends obviously on the state of the system, minus temperature of the reservoir times entropy of the system, which is a function of its state, plus pressure of the reservoir times volume of the system. This new function is called the free enthalpy. And for this situation, where the system is kept at a constant temperature and pressure, we find that its equilibrium is characterized as the minimum of free enthalpy. Up to this point, we've always kept the particle number fixed. Let's finally consider a situation where this is no longer the case, but where the system is coupled to a particle reservoir. More precisely, let's consider the situation now where the system is coupled to both a thermostat and a particle reservoir. The particle reservoir fixes the chemical potential. This means, in this schematic representation, that we have a reservoir at fixed temperature and fixed chemical potential coupled to our system. The system still has fixed volume, but no longer fixed particle number. And with the reservoir, it can exchange energy in the form of heat, and it can also exchange particles. A system whose particle number is not conserved, and a system which can exchange particles with an external reservoir, is called an open system. Following our general scheme, equilibrium is characterized at fixed total entropy as the state which minimizes the total internal energy, so the variation of system internal energy plus variation of reservoir internal energy must be larger than zero. Again, this is the common trick. We combine system plus reservoir into a composite system which is now isolated. And here we use the fact that the variation of the internal energy of the reservoir equals the temperature of the reservoir times variation of the entropy of the reservoir plus the chemical potential of the reservoir times variation of particle number of the reservoir. And once again, since the total entropy is fixed, the variation of the system entropy is minus the variation of the reservoir entropy. And since the number of particles is conserved for the combined system, the variation of the number of particles in the system must equal minus the variation of the particle number of the reservoir. And finally, since the reservoir maintains constant temperature and pressure, they don't vary, so this is equal to 0. So always following the same scheme, we find that our extremization principle now takes the form that the variation of system internal energy minus temperature of the reservoir times system entropy minus chemical potential of the reservoir times number of particles of the system must be positive. The function inside the square bracket is denoted by A. It depends on the two parameters that are fixed externally by the reservoir, so the temperature of the reservoir, the chemical potential of the reservoir, and It also depends on the volume, which we also keep fixed. And then, of course, it's a function of the state of the system. And it's defined in the following way. It's the internal energy, which is a function of the state, minus temperature of the reservoir times the entropy, which is a function of the state, minus the chemical potential of the reservoir times the particle number of the system. And this function is called the grand potential. And in this situation, we find that equilibrium is singled out as the state which minimizes the grand potential. This concludes the presentation of the thermodynamic potentials. We will work with them for a while, but here is how they appear in thermodynamics and under which circumstances they are relevant. It's always a bit tricky to remember all these thermodynamic potentials. Unfortunately, there's this nice mnemonic device of the Guggenheim square, which we can also use for the thermodynamic potentials. In fact, there are two of them. The first Guggenheim square has this form. In the corners, we have the thermodynamic potentials. We start in the top left corner with the free enthalpy, and the thermodynamic potentials are defined for arbitrary states of the system, not necessarily equilibrium states. So the row featuring in here is the state of the system, and it's not necessarily an equilibrium state. We will later make the special choice that these are equilibrium states, but at this point we are not yet assuming that. So on the top left corner we have the free enthalpy. In the top right corner we have the enthalpy. Lower left we have the free energy, and lower right we have the internal energy. Then on the sides we have here the pressure of the reservoir, the temperature of the reservoir, the volume, and the entropy of the system. So the corner is the potential to be minimized if we seek equilibrium. Now each corner has two adjacent sides. So for example, the free energy has two adjacent sides, namely the temperature of the reservoir and the volume. These are the parameters that are controlled externally, controlled or fixed. Yeah, so as an example, top left corner, free enthalpy. This applies to the situation where the system is coupled to both a thermostat and a volume reservoir. So both the pressure and the temperature are controlled externally. They are fixed. They are maintained by the reservoir. And indeed, in this schematic representation of the Guggenheim square, the free enthalpy has as its adjacent sides the pressure of the reservoir and the temperature of the reservoir. So these two are controlled. And under these circumstances, it is the free enthalpy which has to be minimized when you seek the equilibrium. You can move from one potential to the next by moving parallel to one of the arrows and thereby adding the product of the two ends of the arrow. So you can go from for example, from the free enthalpy G to the enthalpy H by adding T times S. Indeed, when you remember the definition of the free enthalpy and the enthalpy, you see that they differ by a term T times S. Or if you want to know, say, lower left corner, the free energy F, how is it related to the internal energy U? Well, you have to go from U to F, so you have to go to the left, anti-parallel to this horizontal arrow. So you have to subtract the product of temperature of the reservoir times entropy of the system. And indeed, the free energy, F, is the internal energy minus temperature of the reservoir times entropy of the system. Yeah? So you can move from one potential to the next by adding or subtracting, depending on whether you go in the same direction or in the opposite direction of the arrow. So by adding or subtracting product of the ends of the arrow. So this is a convenient way of memorizing some of these relationships. What I have to caution you about, though, is that in contrast to the Guggenheim squares that we have encountered so far, it is not the case that you obtain the opposite end of an arrow, so the conjugate of one of these variables, by taking partial derivatives. So it's not the case that in this scheme that when you take the partial derivative of the free enthalpy G with respect to pressure, that you then obtain the volume. This is true when we are in equilibrium. So this comes later, yeah? So then this is true again. But here we still allow non-equilibrium states, and as long as we allow non-equilibrium states, this is not yet the case. Yeah? So obtaining conjugates via partial differentiation requires equilibrium. I should add up here that this relationship between the potentials, where you can add and subtract products of the ends of the arrows, this holds also for non-equilibrium states. But this other convenient property of the feature of the Guggenheim square, of the previous Guggenheim squares that we have met, that you can obtain conjugates by partial differentiation, this doesn't hold away from equilibrium. This holds only if you are in equilibrium. Now, to help you even more to memorize this particular Guggenheim square, there's a very nice sentence. If you start from the top left corner and go clockwise, we have G, P, H, S, U, V, F, T. And a nice sentence that can help you memorize this sequence is: good physicists have studied under very fine teachers. There are other versions of that, but this is the sentence I like most. This is one Guggenheim square, and it's the better known of the two. There's another one, you can draw another one that also includes the grand potential. The Guggenheim square up there always presupposes that particle number is fixed throughout in all these cases. Now, if we allow exchange of particles, then we are in a new situation. And you can draw a second Guggenheim square, and there's no such nice sentence, at least I don't know any such sentence. Maybe you can invent one. It looks as follows. There, the free energy is in the top left corner. The internal energy is in the top right. In the lower left, you have the grand potential, and the lower right is empty. And then on the sides, you have particle number, temperature of the reservoir, entropy of the system, and chemical potential of the reservoir. And again, the same remarks hold as for the upper Guggenheim square, that the potentials are related by these arrows, and obtaining conjugates via partial differentiation is possible in equilibrium only. That's a feature that we will look at, and we will also verify with an example next week.